Yes.
So now, let's continue our discussion. Yesterday we talked about the degenerate perturbation theory, and we formulated that theory and we obtained the result of degenerate perturbation theory. And today's target is basically, let's go with a couple of examples, and because through examples we understand better, solve a couple of problems. Okay, so that will be our target. So to start with, let me choose a problem. Suppose I have an eigenstate, say eigenstate 1 and eigenstate 2. And what I do is I incorporate a perturbation. And let me assume that perturbation to be HP. And this HP is, say for example, it is lambda 0, 0, 1, 1. Okay? So we have a degenerate system. In this degenerate system, where we have two eigenstates, okay? I name eigenstate 1, eigenstate 2, and I introduce the perturbation, and that perturbation is defined by this matrix, right? When lambda is a constant, its value is very small, right? Now the question is, we want to calculate the correction. We want to calculate the correction in the energy. And in addition to that, what we obtain basically when we introduce the perturbation to our system, we come up with discrete energy eigenvalues. That means your perturbation lifts the degeneracy of your system, right? Now, how will we solve that? We know from yesterday's lecture that you have to diagonalize your system, right? And what's the best way? How we can do that? You remember that determinant of this HP minus, let me choose epsilon as the energy, and I is an identity matrix. This determinant should be equal to 0. This is how we do it, right? Now, for HP, what I have lambda, determinant of 0, 1, 1, 0. Then we have minus epsilon. I can write down the identity matrix as 1, 1, 0, 0. And this should be equal to 0. Getting my point? What you have? You have a perturbation in the form of this matrix, a 2 by 2 matrix. Okay? And you are acting that on your system as a perturbation. So, what do you expect from this perturbation? What do you expect? You expect the degeneracy. You expect that you will have discrete energy values. They'll be different from each other. Right? Okay. Is this clear? Can I move on? Okay. So, from here, what I'll get 0, 0, lambda, lambda. So here I will have 0, 0, here you will have lambda, you will have lambda, then minus, you will have epsilon, epsilon, 0 and 0. And this is equal to 0. Clear? Okay? So, now subtract the 2. What you will get? This is 0 minus epsilon, this is minus epsilon. Lambda minus 0 will give you lambda. Lambda minus 0 will give you lambda. 0 minus epsilon will give you minus epsilon. Now finally you have a determinant, okay? And this determinant should be equal to 0. Now this should be equal to 0. So from here, this will give us epsilon square minus lambda square is equal to 0. So you have a quadratic equation. And if you have a quadratic equation, this epsilon will have two values. So what you have seen, you have lifted the degeneracy of your system. So what you obtain from here, you obtain epsilon is plus minus lambda. Are you getting? So you had an unperturbed epsilon. Now you have calculated the correction. And what will be your new energies? Epsilon 1 will be what? Say epsilon naught was unperturbed plus lambda. Okay? You may call it epsilon 1 for the time being. No. Epsilon, I will call this E1 here, so that I can differentiate the two. I will use it as E1. Here I will have epsilon 1. So E1 will be E0 plus lambda. And what will be another value of energy? E2. That will be E0 minus epsilon 2. So what will be E2? E2 will be E0 minus lambda. Is it clear? Got it? So what you have done? What you have seen, you have observed that the degeneration of your system is lifted, and you have two different values of energy, E1 and E2. Clear? Any problem? Now, let's go with, let's take another problem. Okay? Let me take problem 2. What I do is, I choose my ideal hydrogen atom problem. Okay? And in that problem, I choose n equal to 2. Alright? What I choose? I choose n equal to 2. Do you know n? What is n? It's a principal quantum number. You remember that? You have 3 quantum numbers in the problem of hydrogen atom. Yeah? Number 1 is principal quantum number. Number 2, orbital quantum number. Number 3, there is no spin in the problem of hydrogen atom. Then you have magnetic quantum number, or you may also call it as azimuthal quantum number. So you have n, corresponding to that n you have L, corresponding to L you have Ml. You remember that? Okay? So this is your problem of hydrogen atom, and for n you will have L equal to 1, and Ml will be 1, 0 and minus 1, because Ml is 2L plus 1 now.
Yes.
Am I right?
Yes.
This is your original undisturbed hydrogen atom. And it has states. The state, I will take on the ket of it as L and Ml, and you will have the bra of it as L and Ml. Clear? Now what I do, I introduce perturbation. I introduce external perturbation. I introduce magnetic field. The magnetic field that I am applying on this problem of hydrogen atom is along Z direction. And I define that as Hp is equal to mu B B L Z by H cross. Okay? So you have the problem of hydrogen atom. You choose n equals to 2 and you introduce perturbation. Now, which perturbation is this? This is time-independent perturbation, right? And you are introducing a small magnetic field. A small constant magnetic field is applied and its magnitude is given by this term, HP. Now I want you to, so what will happen? What will this perturbation do to your n is equal to 2 level? What will it do to that? It will lift the degeneracy. Because as long as your knowledge is concerned, this ML, 1, 0 and minus 1, they have the same energy. Are you getting my point? Yes? This one, it's mu B. It's a Bohr magneton. Okay? B is the magnetic field. LZ is the Z component of angular momentum, right? And H cross is your reduced Planck's constant. Now, I want to solve this problem.
Yes.
Can you solve it?
Yes.
Come on. Okay. So we have a problem here. We want to calculate the lifting of degeneration. How does this perturbation that we have introduced here, how does it work in our problem? So what will we do? Come on, how will we do this? Yeah. Come on. You remember your problem of angular momentum? If you have LZ acting on psi, what you are going to get out of it? Come on. Now this LZ is an operator. You have H cross and L, and you will get your same state. This is the basic argument that will play a very important role in calculating the degeneracy, the lifting of the degeneracy in our problem. So I have the two states. I have the state L, ML. It will lead us to ML, H cross, L, ML. Am I right? Now what we have to calculate? We want to calculate the correction. And how we calculate that? We calculate the matrix element of the perturbation in the framework of what? In the framework of the known eigenstates. This ML and L is known to you. You have solved the problem of hydrogen atom. It's your psi and naught. Psi and naught. Are you getting my point? So, from here, what I want to calculate? I want to calculate basically the matrix element of L, ML, HP, L, and L. This is what I have to calculate. Right? Now, what is your HP? Your HP is given in the problem. So what's that? So you will have L, ML, then you will have mu B, then you will have B, then LZ by H cross, you will have L, ML, and close it. Clear? So this mu B is Bohr magneton, get it out. Magnetic field is constant, get it out. H bar is out. Inside you are left with L, ML, LZ, L, ML. Am I right? Getting? You're getting it? Okay? You should feel happy about it because you're getting it. Okay? So now you have energy eigenvalue problem here. You have LZ, L, ML. It will give you what? ML H bar. So you will have mu B B by H bar. Then you will have L, come on, you will have L, ML, and you will have ML, H bar, L, ML. Am I right? You can see this H bar and H bar will go. This ML is a constant, right? This ML will come out. So if this comes out, it has three values. ML has three values. 1, 0, and -1. So, can I move on from here? Yeah, you have mu B, B is out, ML is out, and you have a situation. ML, L, ML. This is already done in the problem of hydrogen atom, and its value is equal to 1, right? So you have the correction here. Mu B, B, ML. Right? So you have E1, you have lifted the degeneracy of your system by introducing the external perturbation. So you have E1, what will be that? That will be E0 plus mu B and B, am I right? What will be the next? E2. That will be E0 plus 0. Right? What will be E3? E3 will be, come on, it will be E0 minus mu B and B, because I'm using the value of ML. So what have you done? You have lifted the degeneracy of your system by introducing a constant perturbation on your system. Is this clear? Okay. Clear? Can we move on? Okay. Now let's choose another problem. And let's use a conventional approach to solve that problem. The problem is the problem of harmonic oscillator. It's a problem of harmonic oscillator. Okay, you have an unperturbed harmonic oscillator, and then you introduce the perturbation. And what am I telling you is the perturbation that I'm introducing, say that is HP, the perturbation that I introduce is equal to lambda x cap square. Right? Okay? Lambda is a constant, and you are introducing a perturbation of x square in your problem of harmonic oscillator. And I'm asking you to calculate the correction, in the energy. You should realize one thing. 99% of the information is in your first order correction. It takes a very good part of correction to your problem. Okay. That's why the most problems are stuck to first or second order. Right? Now the point is, you have this problem, how will you solve it? Come on, what you will do? You will calculate its matrix element, or you will calculate its expectation value. And there are different ways of solving the same problem, right? And we can choose our basic harmonic oscillator problem that we have, and we have the ground state wave function for harmonic oscillator problem, right? Can you tell me how much is that? If I represent that as, say for example, psi of x, does any one of you remember that equation? Yeah, what is that? That is m omega by pi h cross raised power 1 by 4 e to the power of minus m omega x squared by 2h cross. This is your eigenfunction for the ground state of harmonic oscillator. And you know the meanings of the symbols that I have reduced in this equation. You know everything about them. M is the mass, omega, pi, h cross. These are the things that you're supposed to know all of these symbols. Now, what am I supposed to do? I'm supposed to calculate this correction to the energy of this harmonic oscillator. That's my job. And for that, I have to calculate the matrix element. Or in this case, I can choose a way of expectation value. Now the point is, how do you calculate that then? For that, you have the same thing. The ket of your side of x, and then you have the perturbation, then you have psi of x. This is it. Okay? This will give me the correction. So for psi of x, what will I use? I will use m omega by pi h cross raised power 1 by 4 e to the power of minus m omega square, omega x square by 2h cross. Am I right? Then you will have the perturbation. What is that? That is lambda x square. And then you will have what? The same thing. M omega by pi h cross. Yes, you are right. It is 1 by 4. You are absolutely right. Raised power 1 by 4. Come on. And e to the power of minus m omega x square by 2h bar. Clear? Fine up to this point? Any queries? This is pure technical kind of things that we are doing here. Now, you can see I can multiply these constants. Okay? If I multiply these constants, what I'll get? You see this will be the square of this. This thing will be multiplied with this. You will get the square and 1 by 4 will cancel. You will get 1 by 2. So what you will have? You will have m omega by pi h cross whole raised power 1 by 2. I think there is no issue in this. Okay? Then the rest of the thing that's there, I will write it in the form of an integral. Okay? And the limit of that integral will move from minus infinity to plus infinity, because you are solving the problem of harmonic oscillator. So you will have integral minus infinity to infinity. Right? Okay? Here you will have e to the power of minus m omega x square by 2h cross. You will have x square e to the power of minus m omega x square by 2h cross and dx. Is this clear?
Lambda.
Yeah. So lambda you can keep outside. That's not a problem. Okay? Fine? Now multiply these two exponentials. The base is same, powers added, 2 and 2 will cancel. So what you will get? You will get lambda m omega by pi h cross whole raised power 1 by 2. Right? Then here you will have integral minus infinity to infinity. So this I can write as x square. Then you will have e to the power of minus m omega x square by h cross dx. Now what is this? It's a Gaussian integral. Okay? And you know the value of this integral. If you have something like this, if you have integral minus infinity to infinity, x square e to the power of minus alpha x square dx, this is equal to under root of pi by alpha raised power 3 by 2. So in my problem, what is alpha? In my problem, alpha is m omega by h cross. So in my problem, alpha is m omega by h cross. Am I right? Am I right? Okay. So I can use this result in the calculations that I'm doing. So you have lambda, then you have m omega by pi h cross raised power 1 by 2. The result of this integral is under root of pi divided by alpha raised power 3 by 2. Come on. Alpha raised power 3 by 2. So I can write this as h cross by m omega raised power 3 by 2. Clear? Okay? So I have changed numerator into the denominator. That's why I'm not changing the sign here. Okay? So you see, instead of m omega by h cross, I have used h cross by m omega. So I'm not supposed to change the sign of the power of this bracket. Okay? So that's why it's 3 by 2. Now, come on. What should I do now? I should rub the top part. So you have lambda, then you have m omega raised power 1 by 2, then you have under root of pi in the denominator, then you have under root of h cross in the denominator for this, then here you have your own under root of pi, then you have divide by m omega raised power 3 by 2, and this is your h cross 3 by 2. Clear? Yes. If I commit a mistake, you kindly tell me at that time. So, come on, you see this under root of pi will go with under root of pi. This under root of h cross, it will go up. It will make h raised power. Yeah, this is lambda. Let me do it like this. This is m omega raised power 1 by 2 minus 3 by 2. Divide by h cross raised power 1 by 2 minus 3 by 2. Is this clear? Come on. Okay, so what you will get from here? Minus 1. In the numerator, you will have a power of minus 1. In the denominator, you will have the power of minus 1. Right? So, can I move on? So, from here, what you will have lambda, then you will have m omega raised power minus 1 by 2 divided by h cross minus 1 by 2. Minus 1 by 2. Right? Now, we can exchange them. The denominator will become the numerator, and the numerator will become the denominator, and you will have a final correction that you were interested to calculate. So you will have lambda h bar, yes?
Minus 1.
Then in both the cases we'll have the minus 1, yes. Yeah, it is minus 1. I did it wrong. So it has to be minus 1. Okay? So finally, this is h bar by m omega. That's it. And you will have seen this result while solving the problem of harmonic oscillator when you introduce the perturbation in your system. Is this clear? You got it? Any queries? So I think if anybody has any question, you can ask me. Yes, come on. Right? You got an idea? Now actually you have to work in a mixed state. When you solve the problem, wherever you introduce the perturbation, you are automatically understanding where you are going, how you are resolving your problem. Your problem is dictating you the result, and that result explains you the physics behind that problem, right? So that's why I'm always telling you, try to solve as much as problems in the same framework, the framework that you are trying to understand, because solving problems will take you to your destinations. You can, in physics, you have many open problems, and if you solve any of these open problems, you will be the candidates for Nobel Prize. So you should think on those levels that where you can certainly make use of your mind. So you can stop it.
Sir, इनका ऑडिट हो रहा है